All right. So in this case, we need to have a continuation still on our transformers. This time working with the short circuit test, we need to understand like how questions are supposed to be given. And our typical approach as we had the first time working with the open circuit test, where we consider that as the no load test. But in this case, this is a short circuit. So what is it that we are supposed to consider on a short circuit test? So we are considering a short circuit test in this case, which is the one that we are now dealing with at full load. Remember the first one? Open circuit, no load. Now we are at full load. So you are considering this at what? At full load conditions. At full load conditions. That is what we are going to have. So with this, it means the output that you're going to have, it'll be now considered as a short circuit. So a short circuit test we are going to have can be, actually it can be conducted on the primary side, and that is placing the instrument on the secondary side. So this is how we're gonna have, we're gonna just have our circuit diagram. Let me just present the circuit diagram, how we're gonna have this time. Remember, on the primary, we're gonna have our voltage there. All right, then we're gonna have our ammeter to measure our current in a series combination like that. Our wattmeter, as we had before, this is gonna be the part of our wattmeter that is given to the what? To the secondary side. So we're gonna have this on the secondary side where we have this time it is going not to be open like what we had previously, but we are going to have this with something that is going to be measured, which is the current. As we considered part of the short circuit, we are going to need the current that is measured on our output there. So we're just going to consider this as our A2. All right, so this part, as I said, our wattmeter as we had before, our voltmeter here, and we're going to have this as our V short circuit. So we are saying this short circuit can also be conducted by a short circuit in the primary side and placing the what instrument on the secondary side, meaning to say we can have our V short circuit on the primary side. A voltmeter is given, also the ammeter one, the wattmeter. These are connected to the primary winding. You're having this on the primary side, while the secondary side is what? Short-circuited using a suitable ammeter. So the secondary side is going to be short-circuited using suitable. That's why we have our A2, our suitable ammeter that is given there. So if a very low voltage is applied to the primary side and this voltage is gradually increased until full load currents flow in both primary and secondary windings, the wattmeter records the power on the short circuit. So we are considering a condition that the voltage is being applied, a very low voltage, to the primary windings, and this voltage is gradually increased until what? Full load currents, meaning to say we talk of the full load conditions until we reach full load conditions. That is where now the flow in both primary and secondary side of what? Of the windings, that full load condition that we are having of the current. So the wattmeter there will be there to measure the power now. This one is measuring the power that we have now, which is considered as our short circuit power. So with this, we are going to consider our calculations that are necessary. As we are talking of the short circuit power, what are the calculations that we are going to have from this short circuit test. Okay, so from this test, we are going to determine these calculations that are necessary. They will need you to calculate the power as we are considering the wattmeter measuring the short circuit what? The short circuit power. Remember now this is closed. Remember we have this. So we are going to have our short circuit power, number one. And consider P short circuit, which is given as I1 squared. That's RE1. Remember, we talked about these values before, where we have to consider these equivalent values. I'm just going to also go through that part to show you, maybe in case that you have forgotten this part, but we talked about this in our previous class. So this is also going to help us again in our calculations. Meaning to say, if we are to considering this from the primary side, we can also consider it from the secondary side. The same short circuit power can be calculated. On the secondary side, we're going to have I2 times RE2 there. This is of the secondary side. We consider on the primary side, okay, another part that you're going to need is the short circuit, which is the reduced voltage applied to the primary side, while the secondary side is what is short circuited. That is the one that you write as V short circuit 1. This is the reduced voltage applied to the primary side while the secondary is short circuited. So it can be calculated from I1. Remember, that's voltage. If you've got voltage and resistance, but the resistance there, you are going to consider this as the equivalent impedance. Equivalent impedance. What about on the secondary side? We are going to have this on the secondary side of the secondary side, meaning to say we are considering the reduced voltage applied to the secondary while the primary is short-circuited. While the primary is short-circuited at that moment. So just like what we have on this one, that's going to be I2 times ZE2. So this is what we are going to have. This is simply power from your copper loss. Remember, talking of the transformer, the copper loss power is what? I squared R. So that's why we still have that same consideration. The issue of the voltage, remember your Ohm's law? Voltage. But now you have to work with the equivalent. That is what you will actually need, which is a condition that is important. And on here, we are also going to have the additional calculations as we had our transformer during the short circuit test. The low voltage winding is normally short-circuited. So meaning to say, in that consideration, in terms of our transformer ratio, since we are considering that during the short circuit, the low voltage winding is normally short-circuited, meaning to say we're going to have this as V1 over V2 is equal to N1 over N2 as we are used to in terms of the currents I2 over I1. But we are going to equate when considered as a short circuit. So it's going to be, because one of the side will be having a short circuit in the presentation. So this will be a V short circuit 1, and we're going to have this one as 2. All right, let's talk about these. Okay, I said the first one, it is simply representing the reduced voltage applied to the primary side. So this is the reduced voltage applied to the primary side. Applied to the primary side. This is what you're gonna need. It is applied to the primary side while the secondary is what? Short-circuited. while the secondary at that moment is short-circuited. While the secondary is short-circuited. So this is the condition that we are talking about. Considering as 2 is just as what we have on 1, reduced of what? Primary, the secondary side, this one. So it's going to be the reduced voltage applied to the secondary this time. So this is applied to the secondary. That is on the secondary side, while at that moment, the primary is short-circuited. While the primary is short-circuited. So these are the conditions that you are actually going to be working with. The primary side is being short-circuited at that moment. So you can actually use that in our formulas as we are to work with our transformer ratio. Also talking about the reactances, remember we had these formulas before. The method of referring, everything is going to be applied. I'm not going to refer to this also, whatever condition that can happen in terms of your calculations. Everything has to be considered as you had before. Remember, we talked about these per unit values. So you're supposed to also remember those. Talking of the reactances, remember how you had from your equivalent conditions here, the equivalent value of the impedance from the square root of RE. We can now make this to be the subject, which is the reactance XE. We can make it to be the subject. Remember your equivalent reactances that we had and resistances. So from that formula, you can even make whatever that you want. So there we just made adjustments on our transformer ratio. Remember that. So everything is just going to remain as it is. So as you heard from this condition, let us manipulate and make XE the subject, because in our calculations, somehow we are going to have this. So also, as a remembrance, you're supposed to remember this part also because it is going to help us. If before you had to calculate the equivalent impedance as the square root of RE1 plus XE1 like that. This time, considering the reactances, they can consider a condition where these reactances are to be calculated, meaning to have to make this the subject. Guys, we're just going to square this side, square this side. That will be ZE1 squared is equal to RE1 plus, oh, this is squared. Remember, these values are being squared here. These values are being squared. Sorry for that. So that is a square there. Meaning to say there's a square here. All right. Let me have this one. So it's going to be R1 with a square plus our XE1 with a square. And we need to make reactance the subject. So definitely going to take this to the other side. That will be ZE1 squared minus RE1 squared, which is equal to XE1 with a square. So you have to remove that square by introducing what? The square root, definitely. So that was going to be the condition of the reactance, equivalent reactance, which can also be for the secondary side, referring to the secondary side. So it will be just the same thing, the square root of ZE2 of the secondary over RE of the secondary with a square left. Do not forget that square. We are just manipulating from what we had before, making the subject of the formula. So we have to refer back to what we had before, which is this part. Okay, remember we talked about this. So with this and other adjustments that we are going to make with our formulas, because we had all these before, that is just going to be a continuation. And also the short circuit power that we are considering, this short circuit power, It can be given on different conditions. Remember, this is our power on what? On short circuit. This is our power on short circuit. It can be referred to as a variable loss. A variable loss. Once they talk about that, they're still talking about the same thing. Same calculation. We use this when calculating our copper losses. Remember, these are I squared R losses. These are the copper losses. So they can ask you that as a full load copper loss. They're still talking about the same thing. Full load copper loss. They're still asking you one and the same thing. That is the full load copper loss. The same power that you're talking about there can be given in that way, meaning to say we need to work with more questions as we are to revise. We need to work with more questions, work with your question papers also. Try and gather up the information in how they are going to ask these questions. So there's a typical question that you're given here, which is an example that you're going to consider. A 75 kVA, once you're given this, remember, what does it mean? That is our transformer rating. So that is part of your exam tip also, that you need to understand that the 75 kVA is the transformer's rating. That is the apparent power. Remember that apparent power, guys. So they were given according to our information. And also this other part that we are given. So that is our S, which is 75 kilovolt amperes. 2,200 over 240. They were given V1 over V2, which is simply 2,200 over what? Over 240. We have V1, we have V2. It's a single phase transformer. Still working with a single phase. Here's the following resistance and the leakage reactance values. Okay, we are given this R1, R2, and so forth. And from that information, they are saying, let us consider our questions. We're going to see that the first part, you're just going to have your normal calculations as you are used to here, guys. These are your normal calculations up to here. These are normal calculations. But once now they talk of the full load this, full load this, full load this. We are now considering, remember, these are conditions of what? The short circuit. So the first part, it was just a repetition of what we had before. A, determine the equivalent resistance and the leakage reactance referred to the primary side. Referred to the primary. What is our RE as it is referred to the primary? Remember, we had these calculations before, guys. Also, XE, it's just a repetition. As it is referred to the what? To the primary side. So what is our RE there? All right. So this one, it was just going to be a straightforward question. Let's just try and see if we're going to win here. So remember, as it is referred to the primary, the equivalent resistance first. The equivalent resistance as referred to the primary is going to be given by R1 plus R2 bar like that, which is given as we're going to consider now the ratio. Okay, so it's going to be R2 as it is times what? The ratio squared, the ratio of the transformer, that's N1 over N2 squared, which I said it can be given depending on the textbook. They can write that part as K squared here. So they can write as R1 plus R2 times K squared, where K represents the transformer ratio. So N1 over N2, like I said, this part, N1 over N2 is the transformer ratio. V1 over V2 is the same as what? I2 over I1. Anything that is equivalent to that. So they can say this is equal to K, depending with your textbook. So the K, which is our V1 over V2, N1 over N2, I2 over I1 is going to be equal to what? Are we having the transformer this in terms of number of turns? No. You're given in terms of voltage there, V1 over V2. So you're going to take the V1 over V2. So let's substitute, guys. Everything is there. Gonna check R1. We have got our R1 is given. So it's just gonna substitute R1, which is 0.4. That's plus R2, which is 0.05. So that's 0.05 into what? N1 over N2. In that case, from what we are given, we are going to use V1 over V2. Okay, so that's the same thing. 2,200 over what? Over 240. Everything raised to the power of 2. That was going to give us the equivalent resistance, and that was going to be 4,601 ohms. So that's it there. That's the first part that you are given. Then let's consider the B part. The percent. Okay, so we still have this one, the leakage reactance. So there is still a leakage reactance to be calculated, referred to the primary side. So that's XE1. We also had our formula from X1 plus X2 referred to the secondary. So meaning to say this is going to be given as what? Going to be X1 plus, just going to write as X2 as it is. Your transformer ratio, guys, N1 over N2 squared. So the reactances were given. Just going to substitute. Talked about this, guys. X1, 0.9, X2, 0.08. So let's substitute our X1, 0.9. Our X2, that's 0.08. N1 over N2, just like what we had here. So it's going to be 2,000 over what? Over 240. Everything raised to the power of 2. And that was going to give us 7,622 ohms as we are to consider as our reactance. So these are the leakage reactances that we were given. Right, so you're gonna have this. Let's just write this aside because just gonna need this somehow. So the first one, remember it was 4,601 ohms from this part. Right, then the leakage reactance 7,622. So this one, it was gonna be 7,622 ohms. All right, so this is what we have there. Let's consider the second question where they want us to calculate the percentage impedance. How are we going to have that percentage impedance? Percentage impedance, it depends because there's a percentage now. They need this as a percentage. Percentage impedance. How can we calculate the percentage impedance? It depends with the conditions that you are given. Let's go through our notes and see which part was going to help us in calculation or in calculating this percentage impedance. Remember, I said if you consider this part here, we had per unit values where we ended up calculating the percentage impedance. If there was percentage resistance and also the percentage of the reactance, we're going to use this, but we do not have this. So you have to consider now the per unit resistance and the reactance and the impedance there. In terms of the impedance, I said the per unit value can be obtained, per unit impedance from this formula, or you can use this formula. It's a per unit value. So when they want you to have it as a percentage, so you're simply going to multiply this by what? By 100%. So that is the condition there. From per unit value, you can have what? You can have the percentage impedance. So that was the actually the formula that can actually help us to find or determine this. Okay, so with this, we are going to have I1, that's ZE1 over what? Over V1, which is our per unit impedance that we are having here. This is our per unit impedance, but whatever that you have, percentage, multiply by what? 100. Are we having these values? That is the question. Are we having I1? We do not have this I1. Are we having V1 from the primary side? We have this. Are we having Z1? ZE1, this is the equivalent. We do not have. So that is where our calculations now have to play a role. From what we just calculated, is there anything that can help us to find these values? That is what we have now from this information. Okay, let's start with ZE, which is our equivalent impedance as referred to the primary. And the other thing is that if you are to consider that, because these are two formulas, remember it was going to be given as I2, so ZE2 over what? V2. Because someone might ask, why are we even using this one? The second one, we're going to be limited in that case because of the information that we are given. What you calculated, you remember you calculated referred to the primary side. These are the ones that you calculated. If we are going to use this side, we are going to now recalculate these RE and for the secondary side. So there will be a lot of calculations to be made there. So instead, continue from what you calculated. If they asked you here on A to have the equivalent resistance and leakage reactance referred to the primary, let's say this is what you're given. They gave you to say it's secondary this time. And the second part now, they want you to calculate this, meaning to say on that condition, work with what? Secondary side. Because you calculated something of the secondary, not to say you have to recalculate for that secondary side. That's why we are seeing this formula here is limited to what we calculated in the first. We are calculated, refer to the primary. So let's continue from there. So that means we're going to calculate first. Let's calculate our Z as referred to the primary side. So that is where now we have to consider, like I said, on our X, we're going to consider sometimes they give us as XE, as we manipulated before. We still remember this. Here they can give us as XE. We manipulated that one, but we are not going to use this here from this one. Sometimes you have to calculate this. Sometimes you have to calculate. There we need the impedance. So we're going to use this one, impedance direct. All right. So that is our condition in that case. So let's calculate our impedance as referred to the primary side. So we saw that from that calculation that our ZE1, which is the equivalent impedance, is going to be the square root of RE1 squared plus XE1 squared, which is of the primary. And these values are already calculated here. These are the ones that we obtained there. So that is advantage of continuing with what you calculated before. So our R is there. That's going to be 4,601 squared plus X is also given. We calculated this. So with this, we're going to substitute our values, guys, on our calculator. That was going to give us something like 8,903 ohms as the equivalent impedance as referred to primary side. That is what we have there. So we now have the Z. We are now left with the current, I1. Where are we going to obtain I1? Remember from what you're given, it is given here that we have got our apparent power. The rating of the transformer S is equal to what? Remember, S is equal to V, considering it's a single phase. So if it is of the primary side, it's going to be V1, I1. We are focusing with the primary side, so we're going to work with V1, I1. If it was the secondary, V2, I2. You need the current on the secondary. So from the rating, calculate I. So we're going to calculate our current from the rating. So calculate, that is I1 from what? From S, which is our rating. So remember, S is equal to V1, I1. So what does it mean? To find I1, simply divide by what? By V1 both sides. So that was going to give us the value of I1, which is S over V1. The rating that we are given, the kilovolt ampere that we are given, that was what? 75 kilovolt ampere, which is 75 times 10 to the exponent of 3 over V1. Remember, from our V1 over V2 here, voltage is 2,200. V1 corresponds to 2,200. So definitely, you're going to divide this by 2,200. That's obtaining the value of I1, which is the current of the primary side, and that's 34,091 amps. We have this current, which is missing on our formula here. the part that was missing is current. So you see your electrotechnics, guys, you write this formula, something is missing, find what is missing, like that, like that. This is the idea. So with this, we can have our percentage impedance. I1, what is our I1? We have to consider that. I1 is equal to 34.091. So this is 34.091 times our ZE. As we calculated this ZE, that is 8, we obtain this as 8.903 over V1. That's our V1, which is what we got in that case. Our V1 is given as what? Our V1, remember, that is the one that we used here, the 2,200. We already given this 2,200. So you're just going to substitute as you are given before this. You're already having this 2,200 as a percentage now, just like that. So if you consider this, we had a part where this was calculated. So they just want you to use that, continue that until you get to the idea of the question. So that was going to give us 13.796% impedance, percentage impedance. We have the percentage impedance. So you have to be very careful. All right. So let's just see some of these values, guys, will need them. And as we can see, our body's messed up, guys. There's a lot of things that we need to consider. And as these boards that we use, guys, they sometimes just do misbehave. So we just need to remove some of these values. Very sorry for that. So you guys, you want us to edit these videos, this, and there's a lot of things, guys. We need to, you are requesting this, another one is requesting that one. So the time also for us editing these videos, guys, is going to be something else. But what we're going to do is to work with more questions. That's the only thing that we're going to do, guys. We're going to work with more questions. So we are very sorry for your presentation. Maybe our presentation, as you present us, maybe try to present Meson African motives to your friend, and you'll be like, the presentation that, guys, we're going to work on that one later on. For now, we need the knowledge that is required for our exams. All right. Anyways, guys, let us quickly see this one. See. The per unit voltage regulation, per unit voltage regulation of this transformer, if it supplies full load at a power factor of 0.8 lagging, the per unit voltage regulation, per unit regulation, not percentage, but per unit. And it's at a lagging power factor at 0.8 lagging power factor. All right. We do understand that as we are to work with per unit, this is, we are not having a percentage. It's the same formula, guys, but not percentage there. No percentage, no. So I talked about this also. Is it on this one? No problem. No problem. I think I left that part in my presentation there, but no problem. We're just gonna work on that formula. If you still remember when we considered this regulation, okay, I worked on that one and on a separate class. So make sure that you watch that video so that you do not have a confusion when dealing with what? The regulation. So the per unit regulation is given as of what we just calculated. We were working with the primary side. So guys, continue with that. Refer to the primary, refer to the primary. Everything was like primary side. So continue with that. Because if you try to use the secondary side, it means now you have to calculate those values for the secondary side, which you do not have. You have to calculate them. So we say this is going to be I1 into, that's RE cos of, so we're going to have our power factor there, plus that's going to be XE1, that's the sine of phi in that case. All right, everything over what? Over V1. We are considering the secondary side. Why a plus? Lagging. Remember, it's plus or minus? Minus leading. So the plus, lagging, power factor. So as you can see, like I said, it's an advantage to use this because we worked with the primary side. So everything is there, almost everything. Consider I1, we calculated that. Consider V1, we are given. We're given this. The equivalent resistance as referred to the primary side, we are given. The leakage one is also given. The power factor, all we just need is to find this one, sine of phi. So where are we going to have the sine of phi? From the power factor, because we do understand that cos of phi, which is our power factor, is equal to 0.8. So what is our angle? Arc cos. So that is going to be arc cos 0.8, which was going to give us something like 36.869 degrees. So what is the sine of that? Sine phi, meaning to say sine of 36.869 degrees. That is the presentation of our sine phi, which is going to be 0.6. So I just encourage you, as it is on your, the answer as it is on your calculator, just write sine answer on your calculator, sine the answer. Okay? I think I presented, guys, this on our introduction, so I hope you do understand what I'm trying to say there. That's per unit regulation. Can be calculated. Per unit voltage regulation can be calculated from the I1. Calculated this. That's 34,091 into, that's RE, the equivalent resistance referred to the primary side, 4,601 times the cos, which is our cos theta, power factor. Remember, that's our cos phi there, which is 0.8. Plus, because of what? The lagging power factor. It's a plus there. Okay? Do not forget that. Leading minus. So what's our equivalent leakage reactance? It was 7,622 times the sine of phi, which is 0.6. That's it. Everything over what? V1. As we consider V1 is 2,200. So everything is going to be considered over 2,200. So that's our per unit voltage regulation was going to be calculated as a decimal, this one, which is 0.128, as a decimal, not a percentage, no. Remember when you calculated, if you want to use the per unit regulation, voltage regulation is equal to percentage regulation over what? Over 100%. Remember, guys, are you going to use 100% here? Then after that, you divide by 100. No, just know that it's a decimal. So there's no need for me to use 100% unless they want a percentage. Then I have to multiply by what? 100%. It's now percentage voltage, percentage. So just like that. So that's it. That's it, guys. That's it. That's it. At a lagging power factor. At a lagging power factor. So the per unit regulation is calculated. Let's just write this. Remember, electrotechnics, guys, what you calculated. What you calculated, it's a continuation. It's a continuation. So this we might need it. 0.128. Let's just write it aside. Let's say the next question. The terminal voltage during the full load. It's a full load condition. So there's V2 there at the output. Remember the last one that we had in our previous class, it was open. So you don't consider even calculating of any V2 there. So in this condition, V2 has to be calculated, the terminal voltage during the full load. This is the V2 that we talked about here when we had these calculations. If you still remember, let's just hope I put that one again. All right, no problem. But I hope I presented these notes, guys. I just thought that this one is just gonna be on this part only. Like, it's not gonna go back to what we had in our previous class. No problem. But I talked about this. I'm just gonna write your formula, guys. Remember, I said this is the new voltage. This one. This is the V2 new at full load. It's now at full load. So this is the V2, the new voltage. So you're gonna consider as V2 new, which we calculated previously. Remember, we said our formula is V2 original, the one that we had initial. What is it that you consider as your V2 from the original condition? There, our V2 here, initially. So this is the initial, this one. Initial value that you're given there into what? 1 minus per unit voltage regulation. Per unit, the decimal, not percent, but that decimal, the one that you calculated. So everything is there, guys. Everything is there. We have the V2 there. We're just going to substitute V2, 240 into what? 1 minus per unit regulation. You calculated this. 0,128. Remember this per unit regulation that you had, 0,128. That's 0,128. So you're just going to substitute that. And with this, you are now having the new voltage at full load, and that was going to be 209,28 volts. That's our new voltage in that case. All right? That's our new voltage. So you have to be very, 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 very careful. Very, very, very careful in that nature. Okay, in case we need this, guys, remember our value. The full copper loss, the full load, take note, full load copper loss. Once we talk of this full load copper loss, we are talking about what? This is our short circuit at full load. Now we consider now the short circuit testing. That is where we talk of this now, the short circuit test, the one that we had here. It is at what? Full load conditions. That is where it is happening at these. How can we determine that? That is the full load copper loss. They can ask it as the variable loss. They can ask this as power on short circuit. One and the same thing. This is one and the same thing. Are you working with the primary side as referred to primary or secondary? All these guys we had as referred to the primary. So it's best that you stick to that. Stick to the primary, the one that you had before here, as referred to the primary. So stick with that one instead of using this. Because you have to calculate I2 there. You have to calculate this one. There is, I don't know if you have time for that. So let's stick to this one that we already have calculated. What is it that we consider there? All right, so that's our full load copper loss on number E, which is simply representing what? Our short circuit power. That's our P short circuit. Using, for open circuit, it's power on no load. When it was an open circuit, well, let's say they talk about an open circuit, they're going to talk about what? Power on no load. When we are dealing with an open circuit, they will say power on, but here we are talking about full load. That's the short circuit power. Okay? So with this, we're going to have our short circuit power. That's I1 squared RE1. Or this could have been written as I2 RE2 squared. That's squared here. But as I said, we do not have calculations that were made on this side. Our calculations were referred to the primary side. So we can have a continuation of that which we calculated before. So that's our short circuit power there. It can be calculated. I1, remember we have it. That's I1 here. It was 34. We calculated this value. Remember 34.091. So it's just a matter of substitution there. If you understand the formulas, guys, you're not going to even worry with this subject because you have to work with what you calculate. Do not calculate something else new on that. Or no. All right. Equivalent Resistance referred to the primary side, we also have it 4.601. 4.601. That's it. We have got our short circuit power, which is the full load copper loss. And that was going to give us 5,347.265 watts. We are referring to the power in what? In watts. Full load copper loss, variable loss, short circuit power, one and the same. All right, that's the condition there. So that was, now we talk of the short circuit conditions now. Full load. This once we have this, okay, in case we're gonna need this power, guys, you must remember that value. All right. The F, the voltage that must be applied to the primary winding in order to circulate. What is that you're supposed to circulate? Full load currents. We are talking at full load. What is the voltage there? That is the short circuit. So we consider this as short circuit one. Remember, I referred these ones before. They referred, as we are to talk about this, V short circuit one, reduced voltage applied to the primary side, while the secondary is what? Is short circuited. So it's gonna depend with what we have. Let's say I have one of these, I can use this ratio. If I have one of these, I can use this ratio. But in this case, we do not have any one. So means we have to think of any other formula that has this. Which formula that is it? Okay, let's go back here. I calculated this, guys. Remember? I1 times ZE1. We have this also. We have this also. All right, so this one, guys, for the sake of time also, and these so many formulas that I have written, I'm just gonna use it. All right, no problem. Let me just continue there. We might have also a confusion later on. Let me just have it aside here. All right, I'm just gonna rewrite aside here, guys. I don't think we're gonna need per unit this one. Let's just remove this one. All right. Guys, you see, there are a lot of things in our N5, N6, so just have to be patient enough as we have to prepare more as we are revising for our exams. No problem. So like I said, F, I'm just gonna do it here. So that's V short circuit. One is gonna be I1 ZE1 at full load. All these, they are calculated. Remember, our I1, we calculated this 34.091 times ZE1, calculated also 8,903. So that was going to give us the voltage, which is 303,512 volts. The reduced voltage applied to the what? Primary side. It is being applied to the primary side. At that moment, the secondary will be short-circuited, must be applied to the primary. G, they want you to calculate the voltage that must be applied this time where? To the secondary winding in order to circulate flow. We are now secondary. This is the one applied to the secondary, this one. Applied to the secondary winding in order to circulate full load. We're talking of the secondary side this time. So as we saw that, we can calculate also this. Okay, let me put it this way. But now, on this one, you're going to be limited because of what? You do not have I2, you do not even the equivalent impedance as referred to the secondary side. Those were the limitations that we had there of using this formula. So you'll be forced now to consider this one, which is relating from the transformer ratio that if the short circuit are there, they can also be used. They can be used because this one is limited. That one is limited, guys. So we have to consider the part which is complete. So the G, in that case, This part is limited. So you're going to consider the second one. So unit of the secondary side. So do we have N1 in this? Do we have this? We do not have. So you're going to consider V1. Because we have that. V1 over V2 is equal to this one. Just like that. We have this. V1 over V2. Remember, that is the one that we are given there. V1 over V2. 2,200 over 240. 2,200 over 240. So it's either you're going to just substitute here, 2,200 over 240 is equal to this, because we calculated it. We have its value here. That is the one that we calculated. So that is now its use. Here, its use. We can substitute that. So that is 303,512 over what? This is over the secondary side. Of the secondary side. Short circuit. So that's it, guys. Gonna just cross multiply this and that so that you can find this, or you could have made this the subject of the formula. It's one and the same thing. 2,200 multiplies our V short circuit of the secondary. The 240 multiplies this is going to be 303,512 times 240. Divide by what? By 2,200, because we need a short circuit. This is the part that we need. Yeah, this is the value that we are looking for. This is the part that we are looking for as we had previously. So meaning to say we have to divide by 2,200 both sides of our equation. Just like that. Okay, this was going to cancel our V short circuit as of the secondary side. From this, you are going to have our answer, is 33.104 volts, something like that, which is simply 33.01 or just 33.11 volts, like that, as of the secondary side. So these are the typical questions that you might be given as you are to consider the short circuit test. As you can see, the part of the short circuit is the one that you're talking about, full load conditions. So this is like your normal questions as you are used to working with a transformer at full load. Only that there will be just like special names, this special name of full load copper loss, this and that. Short circuit test. Nothing has changed. What we had before. The calculations as we had before. Let us refer those ones in addition to what we had. So next, in another question, they'll ask you, refer it to the secondary side. You work with that of the secondary side, you work with that of the secondary side. Whatever that you're having is of the secondary side. So try to maintain that also, because they asked you about the secondary, you maintain that. In this question, they asked the first, referred to the primary. So the values that we got, because they are of the primary side, we had to maintain even the values there, continuing with idea of the transformers working with the primary side, because the information here, the first part, they said these values, they are supposed to be referred to the primary. So instead of you now calculate, guys, it's exam, you'll be an exam. You want to calculate this, you're wasting time there. So work with what you calculated. Make it be, let it be a continuation in that manner. You continue from what you just calculated, you find this, from what you just calculated, you find another one. So that is the exam part. So let's just revise, like I said before, as much as we can. Where there are questions, let's add more on the comment section. And thanks for the membership people who are supporting this channel. So that is the most important part, that we had this class. It is because of the membership. So for those who are part of membership, we are so thankful for supporting this movement as we are moving on as Maths on African Motives. Till we meet again.